I will turn it over to Chris.
All right, thank you, Howard, and good afternoon, everybody. Thank you for joining today's webinar, Geologic Hazards 2, Geology for Engineers. My name is Dr. Chris Kelson. I'm a senior geologist here at Atlantic Testing Laboratories. Here at ATL, I do anything and everything related to geology in general, rocks, minerals, and also some building materials and concrete analysis. Anyway, thanks again for joining us today. This is part 2 of the Geologic Hazards series, and in case you missed part 1, don't worry. Part 1 and part 2 are independent of each other, so you can see one without the other, and they both make equal sense. So it's all good. As Howard mentioned, just a few housekeeping issues. We welcome comments or questions throughout the presentation. Feel free to send those via the chat button to Howard, and at the end of the presentation, we'll hear them. And also throughout the presentation, there will be several really difficult questions that you need to answer. They're timed, so you have to answer these things within a set period of time, and of course those are necessary for your to receive your PI credit. So those will be interspersed throughout the presentation. And also, because I do not have a laser pointer to use for everybody, the best thing I can do is use my mouse cursor, which you can see moving around on the screen. So with that being said, let's start the webinar. Okay, so first let's just do a quick definition of what a geologic hazard is. Any earth material, geologic event, or geologic process that is hazardous or potentially hazardous to either life or property. So earth materials, of course, would include soil, water, minerals, rocks, etc. Geologic events could include any sort of mass movement of earth material like landslides, rock slides, so on and so forth, earthquakes, volcanic eruptions, etc. And geologic processes can include weathering of rocks and minerals, erosion, formation of karst, etc. The purpose of the presentation today is basically to underscore the fact that it's best overall to identify identify geologic hazards and institute some sort of mitigation to prepare for them when they happen, versus reacting to them and trying to remediate them or their effects or repair the effects of them afterwards. So again, this is just preparation through identification. Today's webinar is going to be about water, and in particular, we'll just talk about just flooding in general, but also rivers and streams. This is obviously a topic that we could talk about for about 6 months straight. So we'll just topically cover some of the big points and some big issues regarding water, in particular floods and rivers. Excuse me. All right, so let's give another definition here of what a flood is. We're simply referring to the general concept that the elevation of water is greater than that of land, and so for the water we're speaking about, it could be a body of water such as the ocean or lakes, reservoirs, streams, or rivers. We can also be talking about the rise of the water table relative to the Earth's surface, and also when precipitation exceeds the ability of the ground to basically soak water into it. Subsurface recharge rate is less than the precipitation, and that of course ties into the rise of the water table itself. So it's important to understand also that flooding is caused or can be caused by both natural and anthropogenic factors. In other words, they could be natural things, or they could be man-made, or a combination of both, or sometimes it's actually hard to tell what's the driving mechanism behind it, but there could be a couple factors. In this webinar in particular, we're going to talk about the following 6 bullet points: climate change, water management, excessive or sudden precipitation, weather, subsidence of the land, and we'll spend some time talking about drainage basins and the characteristics of them, and that will include a little bit of a discussion on rivers and streams. So without opening a huge political can of worms, given the fact that climate change is a big buzzword these days, I'd like to just take a second or two here and review climate change from a geological perspective to help put things into perspective when we're talking about the weather and climate in general. When we talk about climate change, the general theory is that, right, the Earth's climate isn't static, and everybody now tends to think that it's just becoming hotter, right, as time is progressing, and the climate is changing overall in that direction. The biggest culprit people tend to point to with respect to climate change is the amount of carbon dioxide in the atmosphere, CO2. CO2 is a bad guy in the respect that it's a greenhouse gas. It's one of the greenhouse gases. In other words, carbon dioxide, once in the atmosphere, has the ability to allow sunlight to penetrate the atmosphere and warm up the Earth's surface, but then it acts as a shield, not letting that heat from the Earth's surface re-radiate back into space. So the more CO2 you have, the more intense that action is, and the warmer the planet's surface will become. An extreme case is, say, the planet Venus, for example, whose atmosphere is 96% CO2, and the surface of Venus is so hot because of that you can actually melt lead on the surface of Venus. Here on Earth, CO2 comprises less than 1% of the Earth's total atmosphere, but it doesn't have to be present in very large quantities to have a pretty profound effect. The reason why we're talking about this is because when we talk about climate, we talk about snowfall, we talk about rain, right? And that all goes into our discussion on water. So that's why we're touching on this. To put things also into perspective, I'd like to draw your attention to the two charts on your screen. The upper chart, the upper graph, is plotting the concentration of CO2, carbon dioxide, in our atmosphere from present day, which is the yellow arrow saying we are here, back to 400,000 years ago. And as you can see, the concentration of CO2 in Earth's atmosphere goes up and down a lot, and it has been for the past 400,000 years covered on this chart. If you look at the bottom chart, which corresponds to the same time interval, you can see that the corresponding global temperature increases and decreases, right, with the amount of CO2. So there's clearly CO2 clearly has an effect on temperatures and global temperature changes. One thing to keep in mind, though, is we attribute climate change nowadays to the burning of fossil fuels, and humans really haven't been burning fossil fuels en masse or for industry or energy purposes since about 1880s, when it really started going. But anyway, about the last 200 years anyway, since the Industrial Revolution. So if you want to back out 200 years off of that top chart, we're still basically sitting at the point of that yellow arrow. In other words, the amount of CO2 that we saw in our atmosphere 125,000 years ago and 325,000 years ago, those spikes of CO2, which in some cases exceeded the present day amounts, weren't because of humans burning fossil fuels. Mother Nature does that herself. So the question then is, where's all the CO2 coming from? And first and foremost, understand, please, that Mother Nature herself is a huge source of CO2. Every volcano that erupts, for example, is spewing out huge quantities of CO2 as one of the gases, along with water vapor. Those are the two most abundant gases in volcanic eruptions. So Mother Nature is putting a lot of this stuff into the atmosphere herself. The temperature of the oceans actually has something to do with sequestering CO2. The colder the ocean water, the more CO2 can be dissolved in it and sequestered. So there are a lot of factors at play here. I just wanted you to keep this in mind next time you hear in the news, the whole climate change buzzword. Understand the amount of CO2 in the atmosphere has been going up and down a long time before humans were really on the scene, burning fossil fuels. So it's natural process. To put this into another perspective, climate change is important because the cooler the global climate is, the more water is then locked up in its solid form as ice and snow, like at the polar regions, for example. And the more water that's locked up as ice and snow, the lower the sea level is. Conversely, the warmer global climate is, the more that ice and snow melts and sea level then rises. If we take a look at the map in front of us, you can, first of all, you can make out the present day outline of the United States, and there's some prominent cities plotted on there, okay? If you were to be here on Earth 18,000 years ago, during the last glacial period of ice age, you can see that the coastline was actually lower than it is today, as outlined there, meaning more water was locked up as ice and snow, so the sea level dropped. And on the other side of the coin, if we were to melt all of the ice and snow on Earth presently, sea levels would rise to the point where a lot of the North American continent would be then covered with water, and that's outlined here. But again, this isn't a one-off. If you were here on the planet Earth 100 million years ago, you would have seen actually that things were pretty warm on the planet Earth back then, no ice and snow, and in fact, the Arctic Circle and the Gulf of Mexico were connected with one another across the interior of the North American continent, giving us this huge inland ocean. So again, climate change has been happening forever. The climate has never been static, and it won't be. Question is, how much does mankind have to play in that, right? Okay, let's switch gears a little bit and talk about how we can maybe help control water, at least on a local level, the level of water on a local level, which would then have an impact on local flooding, for example. Water management is what we're discussing, and the example I'll use here is the Racket River. For those of you in New York State, the Racket River is the third longest river totally within New York State. It's 146 miles long, and it's notable because it's been dammed up in 27 different places, and each one of those dams is used to generate hydroelectric power. But the amount of water moving along the Racket River is therefore controlled by these dams. So we're managing the water here, and in times when there's heavy precipitation or heavy snow melt, right, a lot of runoff, and the water level rises, we have the ability to open the dams up and let more water through versus not. So here we can actually kind of control, again, the water level or mitigate flooding by doing so. Excuse me. Talk about weather for a minute. We're talking about rain in this case. This chart is telling us that from 1958 to 2012, so this is these data are about 8 years old or so. Recorded downpours, events of heavy precipitation are increasing across the country, and you can see that the Northeast has actually experienced a 71% increase in heavy downpours. In fact, everywhere across the country is experiencing more rain than noted before during that span of time. So again, we talk about flooding. We're talking about the interaction of water and land, right? So we're just getting more out of the atmosphere than we have. And again, who knows what's driving that? But that's the case. Along that same note, we can discuss flash floods. By definition, this is when we have a lot of precipitation over a short period of time, and the ground just can't absorb all that water, and so the water doesn't soak into the ground. It's just all overland flow essentially, and we call that a flash flood. And in the desert the drier, the desert portions of the country, that's an issue. And people die because of thunderstorms that happen 20 miles away from them, but all the water rushes into them and they weren't expecting it. So again, it's an indicator of excessive and sudden precipitation. Okay, question 1, please.
Okay, Chris, go ahead.
All right, thanks, Howard. Okay, so question 1, which of the following is considered a greenhouse gas? Of course, that's option C, carbon dioxide. Touching a little bit more on weather and storms in particular, we're often at the mercy of Mother Nature, again, deciding on when and where to unload a lot of precipitation over a short period of time, or maybe push water from a set body of water onto land, right? And that wouldn't normally happen unless during severe weather events. The map in front of you is a map of downstate, where we're talking about flooding as a result of hurricanes. So in this case, we have strong weather events, a lot of wind that's pushing ocean water onto the land. And depending on the category of the hurricane, any hurricane, red indicates any area that'll suffer flooding via this method through any hurricane, or orange or yellow if it's a category 2 or 3 hurricane. You can see that different parts of the land will flood with higher and higher strength winds. So again, we're talking about the surface of the land staying put. Lower elevations are more susceptible, obviously, than relative to the higher ones when water starts getting pushed onto them. So having access to maps like this would be helpful if you were buying property or investing someplace into someplace. You need to know if you're a risk for this sort of hazard. On the flip side of that idea, what if the water level, the surrounding water level, say the ocean level, is actually staying static, but the land is sinking? Right. Either way, the result is the same. The water elevation is getting higher than the land elevation, and here's the flood. A good example of this in the real world is Venice, Italy, where the city is slowly subsiding into the ground and, of course, flooding. The reason for this is that Venice is built on an old swamp, loose, unconsolidated, wet swamp sediment, and which just isn't supporting the weight of the building, so all the buildings are slowly sinking into it. And that, in conjunction with a lot of groundwater being pumped out of the same sediments, is causing the land to subside. Let's switch gears again and talk a little bit more about watersheds, otherwise known as drainage basins. And there are several aspects of watersheds that we're going to discuss that have an impact on the interaction of water, both on the surface and in the subsurface of these areas. So a quick definition of what a watershed is, again, goes by the same name of drainage basin. A drainage basin or a watershed is essentially an area of land that's separated from another area of land by some sort of topographic divides. So the area of land, first of all, isn't defined. It could be it could be 1 square mile. It could be half a square mile. It could be 1,000 square miles. The size is irrelevant. But the point is, you have either mountains or ridge lines or hills or something that separates one patch of the Earth's surface from the other one. So the diagram in front of you We can see one drainage basin in this kind of a light green color, and the adjacent drainage basin in this darker green color, and they're separated by this topographic high point, this ridge line, this divide. Within each drainage basin are miniature drainage basins, if you'd like to think of it that way, where you know, each part of each drainage basin is subdivided into smaller ones, and each drainage basin has a small river or stream that basically funnels all of the surface water that falls into that drainage basin part out of it, and that stream then coalesces with the one next to it downstream, and so on and so forth. So again, on the diagram in front of you, this drainage basin that's in the light green color, all of the surface water then is essentially drained out of this singular river or stream. But again, if you walk up the drainage basin, you can see it's being fed by several smaller streams and rivers that are servicing smaller drainage basins within that larger one. A bit of nomenclature right off the bat. Stream or river are used fairly interchangeably. In this discussion, I think I'll be using the term river more than stream. If anybody's curious about what the difference is, I've heard several. Some propose that the use of river versus stream, depending on the size of the feature, a bigger body of water flowing in a singular channel, you'd call that a river. If it's smaller, you call it a stream. Other people tend to define the two by saying a stream it doesn't have to follow a set permanent drainage basin valley. Anyway, they can be used interchangeably. Just that's somehow they're differentiated from each other. Okay, so now you know what a drainage basin is. What we're going to do is pick this apart and talk about the surface of drainage basins, and also how the surface of the drainage basin and the type of soil or sediment within it is going to affect not only the river being that's flowing out of it, but also the recharge of the aquifer beneath it. So on a basic scale, on just a basic idea, I want you to kind of picture in your head two different scenarios of what this drainage basin could look like. Say the drainage basin on the left could be essentially just a big paved area, big parking lots, a lot of roads, a lot of sidewalks, asphalt and concrete. That won't allow, if you can imagine a lot of asphalt and concrete getting rained on, right? A lot of most of that water isn't going to soak through the concrete and asphalt. It'll be funneled directly over it into the nearby storm drain. So you're not going to have a whole lot of recharge at the aquifer beneath it. That big overflow of overland flow of water, because it can't soak into the ground, could potentially cause flooding issues, right? Because you've got a large volume of water with nowhere to go other than over the Earth's surface in specific areas. The drainage basin on the right, the darker colored one, just imagine it being covered not by parking lot, but instead, how about it used to be forest, but now it's been burned down. So just sediment, just bare sediment exposed to the atmosphere. Without the both of those scenarios aren't. Neither one of those scenarios is good, and they pose different hazards for different reasons. For example, if a drainage basin is not forested, all the vegetation is gone. Again, say a big forest fire or a brush fire. There are no tree or plant roots to anchor the soil in place. So whenever it rains, whenever the snow melts, there's nothing holding the sediment to the hillside, and it'll just run over the surface down into the nearby streams or rivers. That's ecologically bad for whatever's living in the stream or river, but it's also a geologic hazard. A couple of years ago, remember in California, there were huge mudslides happening in areas that just were deforested by big forest fires, and towns were destroyed and people died because of it. So again, geologic hazard. In the case of drainage basins that are completely paved over, I think this picture illustrates that fairly well. Imagine we're looking into a drainage basin. Every drop of surface water that falls here is going to be funneled directly into this canal, which is our river or stream here. Needless to say, whatever is on that concrete, cigarette butts, aluminum cans, dirty diapers, whatever's there is going to get washed right into the river, and that's going to affect the quality of the river, water. But also, you know, a lot of water not being able to soak into the ground and not able to recharge the aquifer, which has implications on other levels, such as, you know, we don't have drinking water so much anymore. The government put this cartoon out, which illustrates that point again. And they use the NSA as the bad guy on this diagram. Anyway, again, anything on that paved surface, you know, from you know, fertilizers and pesticides to gasoline leaking out of and oil leaking out of your cars, brake dust coming off your rotors. It all gets washed into the storm drains, which then go directly into the nearby rivers. And you know, next time you're out taking a walk, take a look at the storm drain covers. You'll see either stamped on them or printed near them. Often you'll see that there's actually a sign that says, you know, don't dump anything in here. It goes right to the river, and you know, of course, whatever goes in there is going to impact the critters living in that water. So the effects of surface water in a drainage basin, again, can be controlled either by humans. If we tended to clear cut everything and pave it over, we're going to affect the amount of water and the quality of water coming out of it here at the outlet, versus if the drainage basin is forested, vegetated, it's not bulldozed over, it's not burned, it's not paved over. Soil is held in place, erosion is kept to a minimum. Water precipitation or melting snow will soak into the ground, recharge the aquifer. The soil or sediment will actually kind of filter that water in a way as it gets down into the aquifer, and we're actually decreasing the amount of water, the volume of water that comes out at the end in our river or stream. So the quality of water is good too. I'm going to take 1 second here and say one thing. I've used the term water quality a few times here. The term water quality is a very subjective term. It depends. Using the word quality is very subjective, and I think the idea is maybe think about what specific use we have earmarked for the water. Depends if it's you know, high or poor quality or not. So if we're using this water coming out of the drainage basin here to drink, then it has to be of high quality, right? Nothing dissolved in it that will hurt us or kill us, no bacteria, right? High quality stuff. If, however, the water coming out of this drainage basin is simply used to turn a turbine to generate electricity, then it doesn't matter so much. So water quality is a very subjective term, as are the terms contaminant and pollutant, which I won't get into, but needless to say, the chemistry of the soil in these drainage basins, which is a function of the rock that's being weathered away in those drainage basins, is going to dictate in large part the chemistry of that too, aside from any man-made factors. So if we're talking about a drainage basin's ability to absorb water and mitigate flooding downstream, we need to talk about these two terms, porosity and permeability, with respect to the soil within that, and rock within that drainage basin. So porosity is defined as the amount of void space or open space in a medium. So whether that medium be loose sand particles or gravel or rock, whatever open space is in that material. the percentage of that open space is the porosity. Permeability on the other hand is the ability of water to move through a medium. With respect to soil, and I'm using the term soil and sediment instead of dirt. Dirt is not an official geology term, and I'm dirt's the stuff that you vacuum out of your car off the floor mats, after in the springtime after winter, and all the slush is gone. So soil and sediment I'm using fairly interchangeably. I'm referring to gravel, silt, sand, or clay particles, right? Bits and pieces of rocks and other minerals have been broken down into various sizes. Those are that's termed clastic sediment. We're talking about the presence of organic matter, leaves and twigs and dead things that are mixing in with the sediment as well. The soil itself, the rock and mineral bits that make up the soil, each individual class or particle can be angular or round in shape. They could be big pieces, they can be smaller pieces, and of course the overall chemistry, the overall elemental makeup of that soil or sediment is intrinsically linked to the rock from which it was derived. And the angularity of the sediment, as well as large or small sizes or both, have a lot to do with our discussion here. So let's take a quick look at the clastic sediments. Don't let the tertiary diagram freak you out. This is simply a plot of silt versus sand versus clay, and each one of those words simply is describing a particle size, and the breakdown of sizes are over here on the left. You all know how big a sand particle is. You've been to the beach, you know how big a sand grain is. Okay, silt's smaller than that, and clay is even smaller than that. Anyway, this diagram is important because it's possible to have sediment made out of just one of these end members. So if you have a sediment made of 100% silt, you would plot it here on the diagram. Sediment that's half silt and half clay would plot here, and so forth. The point I'd like to make on this diagram is in the center, we have a sediment type called loam, and by definition, that's an equal mixture of silt, sand, and clay. And there are some common outliers around that too. So these are all of our classic sediments that comprise the soil. With respect to the porosity of these sediments, we're talking about loose sediment. Dark blue is high porosity and white is relatively low porosity. You can see that every sediment type has a high porosity. Each one of those sediment types has a lot of open space in between those sediment particles that can store water. On the flip side, not all sediment types have high permeability. In fact, clays or clayey sediments have very low permeability. So they have the ability to store water, for example, but they won't let the water flow through it. Silt and sand, on the other hand, have the ability to both store water and let the water flow through it. By definition, we're describing sediments that can be aquifers, silt and sand, versus aquicludes or aquatards, which are clays or shales. Okay, question 2, please.
Please continue, Chris.
Okay, thanks, Howard. So question 2, the ability of a fluid to move through a medium that's defined as permeability. Okay, just to finish up our discussion on sediment and sediment particle sizes and how they interact with each other with respect to porosity and permeability. On the upper part of this diagram, I'm showing sediments of different sizes that are mixed together in various proportions. So depending if you depending if you speak geology lingo or engineer lingo, the engineer terms are on the top. So the diagram on the left, where all the class sizes are essentially the same, poorly graded or well sorted, and you can go across and see the differences between them. Each one of those scenarios impacts the porosity and permeability of the sediment in different ways. To show that, take a look at the gray spheres in this diagram on the left. Here we have sediment particles that are all round, not angular, but they're spherical and all the same size, and they're stacked together in what we call a cubic packing order. In this situation, that sediment would have a porosity of almost 50%. In other words, almost 50% of that material is actually just open space in between the grains. If we have a mixture of sediment sizes, so we have our same gray spheres, bigger spheres, but we have smaller guys occupying the void space in between them. Obviously, we're decreasing the amount of open space here, and the porosity would then be about 15% in this situation. So think about these two end members as our sediment in a drainage basin, where the drainage basin is trying to absorb a lot of rainfall. You know, which one is going to absorb more rain into the surface versus not so much, and flooding will result sooner. Let's play this game one more way, a different way to play this. What if we take our gray spherical sediment particles and stack them amongst each other in this fashion? This is what we call rhombohedral packing. This scenario brings the porosity down to 26%. It's about half of what it was for cubic packing. On the right side of the diagram, we're then introducing smaller particles in amongst the larger ones that occupy the void spaces, and the porosity is decreased even more to about 10%. So there's a lot to a soil's ability to absorb water, and the more it absorbs, the less flooding is going to happen, right? So it's not only a function of the size, not so much a function of the size of the sediment, but is it all the same size sediment, and angularity comes into play as well. Those discussions were about soil. I'm going to take one slide here and talk about solid rock. And rocks, when rocks are born, right, they have an intrinsic or primary porosity to them, as well as an intrinsic permeability. So every solid rock has some ability to store water and also let water flow through it. In the case of a sedimentary rock, say a clastic rock like a sandstone, both the porosity and permeability is pretty good. Sandstone makes a great aquifer, can store water and let water flow through it. In the case of an intrusive igneous rock, say granite, for example, that's a very poor, that has very poor porosity and very poor permeability. There just is no open space in between those interlocking mineral phenocrysts. In the case of a metamorphic rock, well, it depends. If the metamorphic rock is foliated, like a schist, for example, or a slate, there's a lot of open space in between the individual mineral grains, and that you could store water anyway. The game changes though if you break these rocks up. If Mother Nature fractures them or faults them, right? Just it cracks them. she cracks those rocks open. Those cracks are now open spaces, as well as the void spaces that were there before. So what was a good aquifer before is a great aquifer now. What was a poor aquifer is now a pretty good one, and And the metamorphic rock, if it wasn't before, it's good now. So secondary fracturing or faulting is definitely a good way to increase porosity and permeability, which will allow those rocks to essentially absorb more water. All right, let's switch gears out of rocks and sediment and talk about the water table. And we've all heard of the water table. Here it is by definition. The table, the top of the zone of saturation, or the phreatic zone. It marks the boundary between the zone of saturation and the overlying area of the vadose zone. So the water table is not the aquifer. It's the top of the saturated zone. And understand that the water table, first of all, is not a static feature. Obviously, it can rise and fall depending on influx of water. Also, atmospheric conditions will let it rise and fall, atmospheric pressure. And also, the water table is not flat. It is to mimic the topography. So if you have a mountainous area, the water table will tend to go up. In valleys, it'll tend to go under it. In the scenario we're showing you here, the water table is, at a certain depth below the Earth's surface. Any bit of melting snow or rainwater will land on the Earth's surface or start at the Earth's surface and soak downward right under the pull of gravity, ultimately toward the water table, and it will become part of the groundwater. Well, if the amount of precipitation here exceeds the subsurface's ability to absorb that water down to the water table, then the water table will rise, of course, and there's a point in time where the water table and the Earth's surface meet. By definition, that's a swamp, right? Or if you've ever been outside on your front lawn after a big heavy rainstorm and you're walking on your grass and it's all mushy and around your feet, the water pulling up around your footprints. Well, the water table and the Earth's surface are the same thing. So again, the ability of the soil or rock to absorb the water depends a lot on, again, our discussion on the sediment class sizes and shapes and so on and so forth. Let's leave our discussion on watersheds and focus now on rivers or streams. And rivers and streams can be classified a couple of different ways. We can have rivers or streams that are called losing, that are losing or that are gaining, and the difference between the two is shown in these diagrams. Each of these diagrams is a cross section through a river or a stream, and the water is flowing out of the screen toward you. The dashed line underneath is the water table. In the case of a losing stream, the water in the stream channel itself percolates, soaks into the bed of the channel, meeting up with the water table underneath. So losing streams are typically not things that flow year round. They're only there when there's a lot of rainfall, for example, or a lot of snow melt. A gaining stream, on the other hand, is actually fed by the water table itself, and the level of water in that gaining stream is the outward manifestation of the elevation of the water table. So the groundwater is feeding that stream. That's called a gaining stream. Another way to characterize or categorize rivers or streams is by calling them either meandering or braided. Either way, we're referring to, again, a body of moving water that's confined to a channel. Okay, so in the case of a meandering river, you can see where it gets its name. It's just meandering over the Earth's surface. Once in a while, the effects of deposition and erosion will work together to essentially pinch off a portion of the stream channel. We then call that an oxbow lake. Right, still full of water, but it's not part of the active channel. In the case of a braided stream, we'd see that it's very typically seen in front of like glaciers, where you have a little bit of water trying to move a lot of sediment. And so this is all one channel, but it's not very deep, and the water is just kind of moving through all the sediment. When you talk about rivers or streams, three things come to mind about the water itself. We talk about the velocity of the water, how fast it's moving, the discharge, how much water is flowing through that stream channel per unit of time, and a water stage, which is the level of the water in that stream relative to some arbitrary point. We can also talk about the erosion of sediment and the deposition of sediment as geologic hazards in the river. So again, we're looking at a cross section through a river channel. The water is flowing out of the screen toward you. The characteristics of a river channel would be that the channel itself that holds the water, the banks which keep it in the channel, and then the floodplain, which is an area that's flattened by erosion when the water level rises and tends to erode past the banks. Here's a real world picture. The Parana River in Brazil. It's a large meandering river, but it has some braided characteristics in places. Here's another one that meets into it. This entire area is a floodplain, and this is a good place to have is to farm and have farm fields, because the sediment is so rich in organics and there's a lot of water. But the bad thing is when the water level rises, you get flooded out. All right, let's stop for question number 3.
Please continue, Chris.
Thanks, Howard. Okay, watershed is another term for drainage basin. When we talk about rivers and streams, we frequently hear the term, well, we not just discuss a floodplain, but then you typically hear of the frequency of flooding that may occur along any river or stream. And so to illustrate this point and how that's determined, again, we're talking about a river or stream here. We're talking about the floodplain on the other side of it, and during flood events, by definition, it's where there's more water trying to move through that channel that can fit in the channel, so it rises up above the channel and floods the surrounding area. The more water there is, the higher the water level will be in the surrounding areas, and that's what we call a stage. So a higher stage means that the water level is just higher, and that corresponds to the amount of water trying to move through that water channel. So when we talk about 50-year floods or 100-year floods, here's how that's calculated. Up in the upper left is an example. So for example, a 25-year flood simply means that in any given year, there's a 1 in 25 chance that a flood of that magnitude will be equaled or exceeded. Okay, it's a 1 in 25 chance. So it's a 4% chance that in any given year you'll have a 25-year flood. On the flip, and again, the flood is defined by the discharge as well as the stage. On the flip side, every year there's a 100% chance that a 1-year flood will happen, right? And there's a 1% chance that a 100-year flood will happen every year. So there's no guarantee that that if you have a 100-year flood one year, you're not going to have another one for another 100 years. It doesn't work that way. It's like you might go 1,000 years without having a 100-year flood, or you might have 5 of them right in a row. So it's just a probability issue. To drive that point home just a little bit, look at this example from North Dakota. The x-axis is the recurrence interval in years, right? So this is time, and the y-axis is the discharge. So it's cubic feet per second. There's a correspondence between the higher the discharge and the frequency. So a 100-year flood equals 25,000 cubic feet per second. That's the equivalent. And all of the 10-year flood, 50-year flood, 100-year flood. There's a 500-year flood, right? That all plot linearly. Notice that two very similar events happened within 12 years of each other. So it's possible. What's that, a 300-year flood? They happened within 12 years of each other. Again, geologic hazard of flooding. If you choose to build your city or town next to a big river, be prepared for it to flood once in a while, and there are the consequences. When we talk about peak discharge and high stages of flooding, here's an example of a picnic table that was high centered on top of a telephone pole in this little valley. The river's down here, but there was so much river water coming through. The level was up here, and that picnic table got stuck on the top. So it gives you an idea of where the high stage mark is there. Stream erosion is certainly an issue, especially for meandering streams where the course of the river water itself will dig or erode out the curves, but at the same time deposit sediment on the other side. If you happen to have a road or buildings next to it, of course you're in danger of your car being picked up and moved by the floodwaters, or your house being picked up off the ground and floated down the river to be high centered on a bridge. Another geological hazard associated with rivers and streams is the sediment around the river channels. This has a high liquefaction potential. It's wet, loose sediment, which will behave like a liquid when an earthquake energy moves through it. Potentially unstable for construction, and because it's loose, it's easily erodible. Good example of this is the Tower of Pisa in Pisa, Italy. This thing weighs 14,000 tons, and it's leaning over because it was initially built on very fine river sediments that are not compacting uniformly, and therefore the tower is leaning because of differential settling. So as far as floods go, how do you mitigate or prepare for them? There's really no way to stop the weather from happening, and you can't really predict how much water is going to fall in any sort of given rain event in the future. So basically, information is the big deal. Even local newscasts will have maps available on their weathercasts that talk about flooding, and they'll identify areas that are at risk for floods during weather. Big weather events. Okay, question number 4.
Go ahead and continue, Chris.
Thanks, Howard. Okay, question 4. What's the probability of a 10-year flood occurring in any given year? So it's a 1 in 10 chance, 10%. Some other maps that can help you identify the potential for flooding. There are maps that exist that tell you how deep the water table is on average. The more shallow the less distance there is between the water table and the surface means that flooding could happen there faster, right? If enough water falls on the surface of the earth and can't be absorbed as fast that the water table can accommodate. Also, maps exist through different states and even cities that describe what they project sea level to be. In this case, in 2050 or the 2100s. Inches of sea level make a big difference, and of course, the low-lying areas will certainly be impacted more by rising sea level. Topographic maps can help, and this is a real world example of clearly a meandering stream. Going over part of the Earth's surface here, you can see this white area is the floodplain that's clearly denoted by that meandering stream. So that's easily identifiable. what's of interest here is this airfield. This is Sherman Army Airfield, Fort Leavenworth, Kansas. So we're looking at a map of Kansas. There's the Army Airfield, and the engineers recognized the danger of the nearby Missouri River and decided to build a levee there to try to block it off. However, haven't been real successful. This is the flooding of that river, right, has occurred 3 times, is listed there on the dates, 51, 93, and 2011. And so this place periodically gets flooded out. Also, we talked about storm surge maps, which areas would be more susceptible to storms of various strengths. And the bottom line is, preparation is the key. Identification of potential hazards is the key. So in any place, identify the potential source of flooding. If you're near a river or stream, obviously that's a no-brainer. Nearby the ocean, that's a no-brainer. To combat rising water levels, dikes, levees, or dams might be employed. Really no way to defend against a rising water table. Not sure, unless you build your house on stilts or something to try to avoid it, but that's kind of a hard one to fight. Also, characterize or at least identify the sediments that you're going to be building on. See for liquefaction potential, for example, or if differential settling. You might try in placing riprap or something to minimize the effects of erosion of rivers. Oops. And also, I guess the bottom line is if you want to avoid getting flooded, you want to avoid floods, don't build where floods can happen. Okay, question 5.
Chris, in the interest of time, while people are answering the question, we have one question that's come in.
Yep.
Who decides that floodplain categories have changed, and how many years of data to say it changed a 100-year floodplain or floodplain, excuse me, to a 50-year floodplain?
Boy, that's a great question, and I'm not sure I can adequately answer that one off the top of my head. I think a lot of it has to do with not only state but also local governments as well, depending on the ground itself, the area itself, and also the federal government has to weigh in on that. The short answer is that's my best answer, but without knowing more about those intricacies, I'm a little gun shy to say. But that's a great question. That's a great question. Point taken.
And you can continue with your slides, Chris.
All right. Thanks, Howard. All right. So question 5. Which state was that Army airfield located? That was in Kansas. All right, folks. That's it for the webinar, and I just wanted to say thank you again for joining us. And